Hello everyone. Today we'll present our work, Scaling Test Time Robustness of Vision Language Models via Self-Critical Inference Framework. In this work, we focus on a critical reliability issue in large vision language models. Even when these models are powerful, their answers can still be unstable or biased by language priors. To address this, we propose a new inference framework called Self-Critical Inference, or SCI, together with a dynamic robustness benchmark called DRBench. Let me start with the motivation. Large vision language models have achieved impressive performance by combining visual encoders with large language models. However, this architecture also brings two important robustness problems. The first problem is language sensitivity. This means that semantically equivalent prompts may lead to inconsistent answers. The second problem is language bias, which is closely related to hallucination. In this case, the model may rely more on language priors than on visual evidence. These two problems reduce the trustworthiness of LLVs. More importantly, previous methods mainly focus on hallucination or language bias, but language sensitivity is often overlooked. Therefore, our goal is to design a unified test time inference method that can improve robustness against both problems without retraining the model. To evaluate these robustness issues more precisely, we propose a dynamic robustness benchmark. The key idea is that robustness failures are not fixed across models. A sample that is difficult for one model may be easy for another model. Therefore, a fixed benchmark may not fully reveal the real robustness limitations of a specific model. Our benchmark is constructed in a model-specific way. Given a target model and existing LVLM datasets, we first evaluate the model and then extract three types of vulnerable subsets. An important observation from the paper is that different models show very different vulnerable samples. For example, the overlap of non-robust samples between Quen and Lava is relatively small. This supports our argument that robustness evaluation should be dynamic and model-specific, rather than relying only on fixed datasets. Now I will introduce our method, Self-Critical Inference, or SCI. SCI is motivated by previous counterfactual inference methods, especially visual contrastive decoding. These methods compare the model's output under the original image and a visually perturbed image. If a token is strongly supported by the original image but not by the perturbed image, it is more likely to be visually grounded. However, existing visual contrastive methods mainly address language bias or hallucination. They do not explicitly handle language sensitivity. SCI extends this idea by introducing two complementary components. The first component is visual counterfactual reasoning, or VC. We create counterfactual visual inputs, such as noise-based or content-removed images, and compare their logits with the logits from the original image. This helps the model emphasize visual evidence and suppress language prior-driven hallucination. The second component is textual counterfactual reasoning, or TC. We create semantically equivalent but lexically different prompts and aggregate their logits. This encourages the model to produce answers that are consistent across prompt variations. The final SCI prediction is obtained by combining the textual counterfactual logits and visual counterfactual logits at the logit level. In other words, SCI does not only compare final discrete answers, it compares and aggregates the underlying continuous logit distributions. We further define three versions: SCI 3, SCI 5, and SCI 7. These correspond to different numbers of inference rounds. This design allows us to study a new form of test time scaling. Instead of increasing the length of reasoning tokens in a single inference, we improve robustness by increasing the number of counterfactual inference rounds. The experimental results show two main findings. First, SCI consistently outperforms strong baseline methods. Second, we observe a clear test time scaling trend. Previous test time scaling usually focuses on longer chain of thought reasoning or more intermediate tokens. In contrast, SCI shows that robustness can also be scaled through more comprehensive counterfactual logit level reasoning. Thank you for listening. Our code is available on GitHub.